Okay, so now we've got the constant acceleration equations to look at. Before we do this lesson, I'm going to go back and take a look at any questions that other my previous courses typically had an issue with from the lessons from yesterday. Uh, Typically, there was nothing out of lesson 2 that caused any issues. Should something change with you guys, let me know and I'll make a post for it. For lesson 3, there was a few. I don't know, we got that. One of the things that students forgot for number 5 here is the greatest distance from the origin. Well, this is a VT graph, so we can multiply the velocity times the time. Basically, the area under the graph is what's going to give you the distance from the origin here. Something important to remember, the area under a VT graph gives displacement, something you should have learned in grade 11 that you may have forgotten. We find the area in here. That's when it's furthest away from the origin. There was some, and then number 8, graphs could look like that. I can't remember if I assigned number 9. Yeah, I assigned number 9. So that graph would look something like this. And then there's the velocity time graph, and I figure we can figure out the displacement too if we want to. Cool. So there we go. Looking at lesson 4 now. This is just, we're going to go through all of the kinematic equations that you guys would have been given in grade 11. So here we go. Final velocity equals initial velocity plus the change in velocity. We know this is true. Vf equals Vi plus whatever the change in velocity is. Oh, I should have all of this. But we also know that the total velocity change is found by multiplying the acceleration and the total time together. So the change in velocity is equal to the acceleration. How is it accelerating times how has time changed? So if I take this thing and I add it to this equation here, I'm going to get something that looks like this. Vf equals Vi plus A delta T, which is first formula that shows up on our formula sheet. So I'm going to start making some notes on here. So hopefully you guys have a paper copy of this. The first thing that we're going to make a note of here is you can see how these things are kind of grouped. We're going to make a section off here. This is going to be our kinematics section, and we're going to add some stuff to the kinematics section over the course of the next couple lessons. The only other formula that's not on here is this guy here. I'll just put that, yeah, I'll make that displacement. So that's the only one we're going to add for the time being. But we've got a kinematic section here. We've just seen our first formula and where it comes from. Moving on. To find the displacement or the distance that the object travels, we can't use d equals vt because that's only true for constant speed. Now we're dealing with constant acceleration. So how are we going to use, or what are we going to use to find our displacement? Well, we do know our definition for average velocity is v average equals total distance. Put a dt there and a total time. What we could do is we could multiply time on both sides. We cancel that there and there, and we're going to get that our displacement is equal to our average velocity times our time. Well, how do you find average velocity? Average velocity is just, I'll go down here, v average equals our first velocity plus our second velocity divided by 2. Well, in this case, our first velocity and our second velocity are our final and our initial velocities. So we're going to get d is going to equal vi plus vf over 2 times t. That's where that guy comes from. We know the acceleration is constant, and we don't know what the acceleration is. We can use this formula. D equals vi plus vf all over 2 times t to figure that out. So this is for unknown constant acceleration. If the acceleration is constant, we can do this. So let's take a look at those two for the time being. Oh, all right, there we go. Using some graphical analysis and some charting. So if we've got an object starting at rest, it's accelerating at 2 meters per second squared I hat. We want to fill in the chart below for velocity and position. We want to draw the location and speed on the number line, and then we're going to graph it. So our time, you could, depends on what Mr. Morrison did when you had this course, but there are labs. There's typically a lab that gets done with this. It's not the toy truck one. There's a lab, there's a lab that deals with this. I'm not sure if Mr. Morrison would have gotten you to do that or not. But anyway, here we go. So we've got, it starts at rest. So at t equals 0, v equals 0. Position is 0, so that's good. And we've got the acceleration there of 2 meters per second squared I hat. So we can fill this thing in here. Time and velocity at 0 seconds, it's 0 meters per second. At 1 second, it's positive 2 meters per second, and then positive 4 meters per second, and positive 6 meters per second. Then we can find the average velocity. Now the average velocity here is going to be, remember, it's initial velocity plus final velocity divided by 2. So my average velocity there is 1 meter per second. And our displacement is I'm going to write this up here. Displacement is vi plus vf over 2 times t. So what I've done here in this column, I've done this part, and I want to multiply it by the size of the time interval to get the displacement from 0 at 1 second. So 1 meter per second times 1 second is 1 meter. Here I've got an interval from 0 to 2 seconds, so my initial speed is still 0 plus 4 divided by 2 is 2 meters per second times 2 seconds is 4 meters times 2, 1 second times 2 seconds. Here we're going to multiply by 3 seconds, and I'm going to have 0 plus 6 divided by 2 equals 3 meters per second times 3 is 9 meters. So this tells us what the displacement is after these different time intervals. So 1 second, we've moved 1 meter. After 2 seconds, we've moved 4 meters. After 3 seconds, we've moved 9. We're going to skip the drawing on this, and we're just going to go straight to the graph. So at 1 second, here we are at 1 meter. At 2 seconds, we're at, oh, sorry, I screwed up. Dang it. I'm just going to use a different color because I don't have whiteout on me. I didn't pay attention to the scaling on my graph. This is 2, 4, 6, 8, 10. So 2, 4, 6, 8. So I should have been down here at 1. All right. At 2 seconds, we've moved 4 meters. So that's that guy there. Started at 0, 0. And at 3 seconds, we're up here at 9. So you can see here what's happening. We've got a line that's curving up. Ignore that dot right there. But for velocities, the velocities are increasing constantly. At 1 second, what's our velocity? Is 2. So the scaling here is 1, 2, 3, 4, 5. So here we are at 2. At 0, we were at 0. At 1, we were at 2. At 2, we are at 4. And at 3, we're going to be up here at 6. We've got a curved line for position time, which we've already talked about. It should be reviewed from grade 11. We have a straight line on our velocity time graph, and the relationship from one to the other For those of you who are going to look at, or who are in calculus, you can get from one to the other by differentiating. Velocity is the derivative of position, which I've said a couple times already today. So curved line on a xt graph, position time graph, implies acceleration. Curving up is positive, curving down would be negative. And we know the slope here. We can figure out the slope, but we know it. The acceleration we know is 2 meters per second squared, so that's going to be the slope of that line there. I believe I have it as part of your homework. Do I give it to you as part of your homework? No, I don't. If you wanted to do it, I don't assign it, but you can do it if you're interested in that kind of thing. You can prove that these relationships hold, that these two other kinematic equations are true. You're going to use VF equals VI plus AT and D equals VI plus VF over 2. You're welcome to do that on your own as an exercise if you'd like. If you want to see it, come on in and I can show that to you, but otherwise you're on your own. So here are the kinematic equations that you would have looked at last year. So now we're just going to use a couple of these as a bit of a review before we start introducing vectors. So we've got an object starting at rest, traveling 12 meters over the next 3 seconds while it's accelerating constantly. We want to find the acceleration and the final speed. So I have an object, don't know what it is, so I'm just going to draw a box. Initially, the velocity is 0. We know that it has traveled some distance. D equals 12 meters. And the time it took was 3 seconds. And we're going to want to find out what this is, and we don't know what this is. So I've drawn my picture. I've got my list of knowns and unknowns. You don't have to put it on the picture. I could have put it over here. I could have done something like this. V initial equals 0. V final equals question mark. D equals 12 meters. T equals 3 seconds, and A is equal to, I don't know. I don't care if you put all the stuff you know into the diagram or if you list it separately. You have to do it somewhere. So let's take a look. We want to find the acceleration of the object. So which one of these kinematic equations can we use to find the acceleration of the object without finding the final speed first? If I go back here and I look, I can use, this is the only one that doesn't require a final velocity. So we're going to use D, this is per part A, equals VIT plus 1/2 AT squared. I'm going to fill it in. My distance traveled is 12. My VI is 0 times T plus 1/2. Oh, I shouldn't put a T there. I should put a 3 there. Plus 1/2 A times 3 squared. Oh, that's 0, so that's gone. So 12 is going to equal half A times 9. So when I multiply by 2, it's going to give me 24 over 9 equals A, which is going to give us an acceleration of 2.6 repeating meters per second squared, which we can write as 2.7 meters per second squared. Oh, sorry. That's it. Done. Here's B. Let's use orange. We want to find the final speed of the object. Excuse me. The final speed of the object can be found. Well, now we can use basically any of the kinematic equations because we have all of the other information. 2.6. Sorry, I need to sneeze. So it doesn't matter which one we use, we can find it. Typically, what I like to do is I like to use equations that don't require information that we've calculated, but it doesn't really matter. If you were here, I would ask you which one you wanted, but you're not, so I'm not gonna. I'm gonna use this equation here. D equals VF plus VI over 2 times T, because this is the one equation that doesn't require us to use information that we've already found. So there's not going to be any rounding issues. So our displacement we know is 12. VF is what we're looking for. VI is 0. It's going to be VF over 2, and our time is 3 seconds. Well, VF is going to equal 12 times 2 divided by 3, which is 8 meters per second. You can feel free to verify that using any of the other equations there, but yeah, there it is. Flip the page. This guy here. So here's a conceptual question for you. An object starts at rest and accelerates east at a constant rate. When it has traveled 10 meters, it is accelerating at a speed v. How fast will it be when it's moving 20 meters? Or will it be moving when it has traveled, 20 meters? I'll select the best answer. Not A, B, C, or D. Well, the first thing we can do is we can eliminate one of those options. We know that because our object is accelerating, option A cannot be true. Because we know the acceleration is greater than 0. But now we need to figure out if it's more than 2v, if it is 2v, if it's less than 2v, or if it's less than 2v but more than v. So we have to figure out what's going on here. We know that, well, we actually don't know anything. One of the best ways to handle a conceptual problem like this is to just start plugging in values and see what happens. And then that will tell us what we should have expected conceptually. And so I'll show you what I mean by that. So we don't know what the speed v is here. We don't know what the acceleration is. Let's just assume some values to be true. Let's say that the speed here, v is 10, and that the acceleration is 5 meters per second squared, and that my velocity was 10 meters per second. Okay? And I'll say here's 1, here's 2. So for the first scenario, we know that the distance traveled is 10 meters. We know that the initial velocity is 0. I've said that v, our final velocity, is 10 meters per second. And I have said that the acceleration is, I don't know what that is. Whoops. Look at my old notes here. Sorry, guys. Right, we don't know what that speed v is. Sorry. We're going to, all we can assume is acceleration. We can assume acceleration equals 5 meters per second. That's what we should be doing. So I don't know what this is. It's going to be 10. We'll show you in the calculation. We don't know what that is. Acceleration is 5 meters per second squared. Let's see what that does. Vf squared equals Vi squared plus 2AD is the formula that we're going to use here, because that's the one that relates acceleration, initial velocity, and displacement to give us a final velocity here. Okay, so final velocity, let's figure out what it is. We've got Vf squared equal, Vi is 0, so that's gone. So we're going to have 2 times 5 times 10. 2 times 5 is 10, 10 times 10 is 100, so Vf equals the square root of 100. So that's the 10 meters per second that we were expecting. But I want to kind of let the cat out of the bag there. We know the acceleration is constant for the entire problem, so let's figure out what the speed is here at 2. Now my displacement is 20. My initial velocity is still 0. My Vf, we want to find what it is right there. My acceleration hasn't changed, though it's a constant 5 meters per second squared. What I chose it to be. So we're going to use the same formula. So VF squared equals VI squared plus 2AD. Write out what we know. Write out the formula, fill it in. VF is going to equal the square root of, that's still 0, so it's going to be 2 times 5 times 20. So VF is going to equal the square root of 200, which is 14.14 meters per second. So my speed here is 10. My speed here, my velocity rather here is 14.14. So how fast can it be moving when it's traveled? Using the example that we had, I just picked a constant velocity. A was 5. You can see here it's 10. Here it's 14.4. This is less than twice the velocity, but more than the velocity. So there we go. We've shown it to be d. We could prove it for all accelerations, and that would be more of a more rigorous mathematical process, but we could do it. Let's do one more example. This one is a little bit more convoluted. Yeah, this is a bigger example, so buckle up. Here we go. We have two cars at rest, and they're facing each other 300 meters apart. There's two sets of information here. I'm going to color code these things. Car 1, I'm going to make blue, and car 2, I'm going to make red. Okay. So car 1 accelerates at 6 meters per second squared up to a maximum speed of 30. Car 2 accelerates at 5 meters per second squared up to a maximum speed of 35 meters per second. So let's first start to chart these things. We're told they both start at rest. We've got 1, but VI equals 0. VF equals 30. The acceleration equals 5 meters per second squared. Here I've got VI equals 0, VF equals 35 meters per second. I should put 5 meters per second in there. And my acceleration is, oh, sorry, this one was 6. All of you screaming at the video. This one is 5. Okay, and so we actually haven't even looked at what the question wants us to find. We want to figure out how long does it take the cars to meet. No, we're not going to assume that they're in different lanes, so there is no crashing. The question we're going to answer is, when do they crash? That's the question we're going to answer, because they're going to. Now, if these are at constant velocity, we could use relative motion, but we cannot use relative motion here because they are accelerating. Because acceleration is not equal to 0. So how are we going to do this? Basically, what we have to do when we're approaching a question like this is, because there's different things happening at different chunks of time here, we have to think about it a little bit differently. What we need to do is we need to figure out what time it takes for each car to reach its top speed. Is the first thing we're going to have to do. For the blue car and for the red car. Well, looking at this information, we can see, yeah, no, we haven't actually calculated it yet. That's okay. We can see here that my, which formula am I going to use here? Sorry, looking back. Let's use this one here. VF equals VI plus AT. My VI is equal to 0, so my time is just going to be my final velocity divided by my acceleration. So in this blue guy here, the the time is going to be the final velocity 30 divided by my acceleration 6. 30 divided by 6 is 5 seconds. And my top speed here, 35 divided by 5 is 7 seconds. So here's what we have to figure out. We have to case this thing. Either they have crashed after this time, sorry, at 5 seconds. By 5 seconds they've crashed. By 7 seconds they've crashed, or after 7 seconds they will have crashed. And we have to figure out what is true based on how far these cars have traveled. Okay, there we go. Case 1 is crash after 5 seconds. And so if they've crashed, that means that together their distances have combined to cover that 300 meters. So let's see if they have. We want to figure out the distance. So it's going to be d equals VIT. I'm going to use this formula here, half AT squared. That's 0. The distance traveled is going to be 1/2 times the acceleration, which was 6, times my time, which was 5 squared. So it's going to be 25 times 6 is 150, and half of that is going to be 75 meters. And my red car is going to have d equals VIT plus 1/2 AT squared. That's 0, so d equals 1/2 times 5 times 7 squared. So that's going to be 122.5 meters. Okay. So we figured out that the total distance covered, I'll use green, is 75 plus 122.5. That is what? 197.5 meters. Therefore, no crash. Okay. So let's see if they've crashed after the other one's done accelerating. Case 2, crash at 7 seconds. This is where things get interesting, because at 7 seconds, up to 7 seconds, this red guy is still accelerating, but now we've got a constant velocity here. So my formulas are going to change. Now I'm going to use d equals VT to figure out the distance covered between the 5 seconds and the 7 seconds. Basically, the reason we have to case this is because they're accelerating for different lengths of time, and so at some point this guy's going to drop down into constant velocity, and eventually this guy's going to drop down into constant velocity too. We just don't know when. Or don't know, sorry, we do know when. We just don't know if they've crashed yet or not. So we're going to use d equals VT, so d equals, that's 2 more seconds has passed, so we know he's topped out at 30 meters per second, times 2 seconds is 60 meters. So we know that d total is 60 meters plus 75 meters, that's 135 meters. So let's look at the red guy. He's still accelerating, so we still have to use d equals VIT plus 1/2 AT squared. Initial velocity was still 0. Distance is 1/2. The acceleration is 5. My time now is 7. Sorry, this should have been 5 squared. Dang it. Slow down to beat off. So this is 7 squared. So this one is now, oh my gosh. Sorry, guys. I'm moving way too fast here. I'm reading my notes improperly. This one was after 5 seconds. So this distance is 62.5. Sorry, guys. So this is going to be 75 plus 62.5. So that's going to be 137.5 meters. This one is my 122.5 meters. So the distance covered is going to equal the 135 from the blue guy plus the 122.5 from the previous guy. We don't add these two together because this one takes into account everything up to 7 seconds because he's accelerated that entire time. So this is going to equal 257.5 meters. No crash. So we know, actually, this is at 5 seconds. So we know that it has to crash after 7 seconds. And after 7 seconds, we can use relative motion again. And the question becomes entirely different. We've now got two cars. Well, not entirely different. We've got car 1 and we've got car 2. I'll color them in here and again in a sec. We know the distance between them. They've covered 257.5 meters, which means that there is 42.5 meters left between them. Okay. We know that this guy is traveling at his final velocity of 30 meters per second. We know this guy is traveling at his final velocity of 35 meters per second. So, and they're going towards each other. Draw that in here. He's going that way. He's going that way. Now we can use relative velocity. V relative. Because they're heading towards each other, we're going to sum them up. The relative velocity is going to be 30 plus 35 equals 65 meters per second. And we want to know how long it's going to take them to cover the 42.5 meters between them. So, T equals D over V. The distance they have to travel is 65 meters. No. Distance they have to travel is 42.5 meters. The relative velocity is going to be 65. So the time it takes, oh, sorry. Wow. Sorry, guys. I'm going to get better at moving things up after the video. So I'm going to pause here. I'll read what I've done. So after 7 seconds, we can use relative motion. The velocity of car 1 is constant now, 30. It's done accelerating. Car 2, velocity is 35. He's done accelerating. They're heading towards each other, and the distance between them is 42.5. They've already covered the 257, and they started 300 meters apart. So the relative velocity when they're heading towards each other, you sum them up. So the time is going to be the distance between them, 42.5, divided by the relative velocity of 65. And we're going to find the time it takes them to cover that is 0.65 seconds. So when do they crash? Therefore, they crash at 7.65 seconds. I'll zoom that out so you can see the whole thing. Sorry, that was kind of rough, guys. I copied some stuff incorrectly. It wasn't rough. It was straightforward, but it was messier than it should have been. That's because you guys aren't in here. And I'm just going from my notes. It'll get better. I'm sorry, guys. So there it is. That's the whole thing. And that's going to be the last example for today, if I'm not mistaken. You're going to have to do something similar in the homework, if I'm not mistaken. Yes, question number 10. Question number 10 is going to be good. So if you flip the page here, your homework is this page here. A little bit. I want you guys to do questions 1, 3, 5, and I want you to do 8 to 11. So 11 is the proof of this guy here. Prove that VF squared minus VI squared equals 2AD. See what you can do with that. Play around with it. If there are any comments, questions, concerns, I will happily assist you. Good luck.